Hi everybody, I wanted to do one more problem with connecting the ideas that we talked about in class today with the connection between the logistic differential equation and the logistic differential function. So the value of k when the logistic differential equation is in this form is the same as the value of k in this thing right here. Likewise, the value of m is the maximum capacity of the population, and that is the same in both. So k is a constant, m will be a constant, and then a will be a constant as well. And the purpose of this video is to show you another example of connecting these two things to each other, and also a little bit about how to develop this thing over here. So let's see how those ideas play out in this context right here. So 4 fruit flies are placed in a half-pint bottle with a banana for food and a yeast for food and providing a stimulus to lay eggs. The carrying capacity of the bottle is 230 fruit flies. The rate of change in the fruit fly population P with respect to time in days is proportional to the product of P and 1 minus P over 230. So find the max. Okay, so let's just stop right there and record some of the things that they told us. So when I see that we had 4 fruit flies are placed in the bottle, we're going to assume they were placed in at time equals 0. So that's when we're going to start our clock. So the population at 0 is going to be 4 fruit flies. So that's a piece of information we get from the first sentence. It says that the carrying capacity of the bottle is 230 fruit flies. So they just told us what M is there. Then they told us that the rate of change of the fruit fly population P with respect to T, so that I think is dP dt, and that is directly proportional to, so that's some constant k, times the product of the population of the fruit flies, the number of fruit flies, and 1 minus P over 230. And that's consistent with having m equal to 30, or 230, because now we're seeing the connection between these two things here and here. So if we transfer some of these pieces of information over here into our logistic function, what we're going to have is P of t is equal to 230 over 1 plus this constant times e to the constant times t. So one of the vocabulary words that your book uses that AP does not, and therefore I will not on the assessment, is in part A. It talks about the maximum daily growth rate. The maximum daily growth rate is not the maximum rate of change of the population, but it is the maximum daily growth rate. They're telling us that that thing right there is going to be the same as what they call K in these two equations here. So what they just gave us was K. K is 0.37. So we can take both of our equations now, both the differential equation and the logistic function, and we can replace the value of K with what they just told us. And over here, that leaves us with only one remaining variable to solve for, and that constant that we need to solve for is going to be A. So if we go back to our original piece of information, that when the population is 4, when time is 0, we can replace P of t with 4. We can replace time with 0. E to the 0 power will just be 1. So really the denominator cleans up nicely. We get 4 equals 230 over 1 plus A times e to the 1. All right, now it's just a little bit of algebra here, and we'll have our value for A. So 4 times the quantity 1 plus A will equal 230. If we divide both sides by 4, we'll get 57.5. Subtract 1 from both sides, and we'll have our value for A. So 56.5 is our value for A, which means we can now write our logistic function here. So P of t, the population at time t, will be 230 over 1 plus this constant we just determined, e to the negative 0.37 times t. So that would be, I think we've done a little bit of the work here. We've got our differential equation, that's this. We've got our logistic function, that's this. This would be the solution to that differential equation. Then it says find the time that it takes for the population to grow to 115 fruit flies. So that's when, at what value of t does the population equal 115? So we're going to set 115 equal to P of t, and then we're going to solve this thing for t. So the rest is just algebra from here. We can multiply to clear the fraction if you like. We can divide both sides by 115. We can subtract 1, divide by 56.5, log both sides to solve for t. And then divide both sides by negative 37/100ths, and that'll give us the value for t. So that would mean in the context of this problem that we'd have about 10.903 days before the size of the population gets to half the carrying capacity. So that, I believe, would also be when the population is growing at the fastest rate. So that would be our critical point when the population is half the carrying capacity. The critical point on the curve then would be at t equals 10.903 and population equals 115. I will attach some practice problems for that for you to work on that are similar to this kind of an issue, and you can let me know if you have any questions. Thanks. Bye.